In this nugget, we get to discuss packet shaping, content filtering, and the role the access point plays in our networks today. Let's begin. I had a friend once tell me that the harder he worked and the more prepared he was, the luckier he was. Which translates into if you're prepared and you work hard, it's very likely that better things are going to happen to you than if you didn't work hard and didn't prepare. And I'd like to apply that concept to this link right here in our network, which is connecting router 2 from our corporate headquarters over to a branch office. They've got a small router over there. And for this link, this looks like kind of a lightning bolt. This is a representation of a wide area network connection. Maybe Las Vegas is where our headquarters is, and maybe this branch office is in Reno, Nevada. So a wide area network provider who has that connectivity is renting to us or leasing to us that wide area network service. And that's often referred to as WAN, wide area network. Geographically separate locations, usually connected at moderately slow speeds. So over here at Acme on the left, we have a local area network or a combination of local area networks that are connected together. And then the branch office, they've got a local area network out here, and we have a wide area network connection that's connecting them together. Regarding preparing, what if this circuit we were leasing from the wide area network service provider, what if it was only 256 kilobits per second, which by today's standards is pretty slow? And with this slow circuit in place, what if we have a whole bunch of traffic all at once that needs to go across the circuit? Maybe we have somebody in this branch office that has an IP based telephone. And this user over here in the branch office with their IP telephone is having a conversation with this user, and this user over here on computer 1 is running some software on their computer that allows that user to use voice over IP. And the acronym of VoIP for voice over IP is the concept of using voice calls but sending the data over our data networks. So back to our scenario, we've got this voice call that's happening. Let's say we have another user, let's say it's Lois here, and let's say that Lois is sending a huge file transfer between her computer and some server that's over here in the branch office. And maybe we're using FTP, which is the name of a protocol for file transfer protocol that can be used to move files. And we have another user here in the branch office, let's say it's Sally, who wants to send a print job over to the network printer at the corporate offices. So we have a telephone call, we have a file transfer, we have a print job, and unfortunately, if this link is 256 kilobits per second, it may or may not be able to handle all of that traffic at once. So how do we deal with that? Well, the secret is to plan ahead. And what we could do is we could set up some type of a packet shaping methodology. So this may be referred to as a packet shaper or a traffic shaper. And effectively what it does, it pre-decides on how we're going to treat this link in the event we have congestion and we can't send everything all at once. So we could prioritize our applications. For example, for voice over IP, what happens if we delay or drop voice over IP traffic between the two users having the voice call? The answer is if we drop enough of those packets or we delay them significantly, the voice application will not work. So I would consider the voice over IP a pretty high priority. Now, regarding the file transfer protocol, what happens if the file transfer protocol gets delayed a few milliseconds or a few seconds? As long as the packets all get there, is anyone really going to notice or care? The answer is probably not. And the same thing could be true for a print job that's happening over the network. For example, if Sally sends a print job over to this printer, Sally's not even in that room. So that print job could be delayed, and no one would know or care that it got delayed by a few seconds. So by using a traffic shaper or a packet shaper, they're both synonymous. We could categorize our traffic as far as high priority, and then perhaps medium priority. And if we had some traffic that we absolutely did not care about, we could classify that as low priority. And then on this link, when push comes to shove, using our traffic shaping, we can give a little bit more bandwidth to the voice over IP, a little less bandwidth for FTP and print jobs, with the goal being that the applications that need that real-time bandwidth can get it, and the applications that can survive a few seconds or a few moments of delay very likely won't even know that it happened. So packet shaping and traffic shaping answers the question of what do we do when there's not enough bandwidth, and how do we handle that? And another term that we often use for categorizing traffic and then prioritizing certain traffic over other types of traffic in the event of congestion is quality of service. So whenever we see the term QoS or packet shaping or traffic shaping, I'd like you to think of unfair treatment. We're treating some traffic better than others in the event of congestion when it happens on the networks. And most of the time, the congestion that happens is going to be happening on the slowest links that are found in our infrastructure. In this case, it's our WAN link between the Acme local area network and the branch office local area network. And that packet shaper functionality, that could be either integrated into the routers, or we might have separate devices at each end that are managing and controlling the packet shaping that's being done across that serial link. In our nugget on the firewall, we touched on several things that firewall can do, including stopping traffic. For example, stopping traffic that's coming in from the outside that shouldn't be allowed in, as well as stopping certain types of traffic from going out, including personally identifiable information, such as social security numbers. We also mentioned that we could do content filtering, so that if a user was trying to go out to a website that's not allowed by policy, we could go ahead and stop that request from ever making it to the outside world. And I don't know if I mentioned it or not, the actual term for doing that filtering, based on the type of website or URL we're trying to go to, that is referred to as content filtering. And I wanted to make sure that you and I had talked about that label of content filtering in association with the function of stopping a user from going to a specific type of website based on policy at our company. So the content filter would be a technical control that we can implement to enforce our company policy. What I'd also like to point out is that if we are using a content filter, it could be a network device, an appliance. So for example, we place that in our network. So here's our content filter right here. And if we had a firewall that couldn't do the content filtering itself, we could train the firewall to go ahead and redirect traffic down to the content filter. The content filter could reroute it back up to the firewall in the event it was acceptable traffic. If it wasn't acceptable, meaning it was denied by the policy set up in the content filter could go ahead and stop the traffic right there and prevent them from going out to that site, which is prohibited through company policy. One of the really amazing advancements in the last decade or so is wireless with Wi-Fi. I mean, we have restaurants with free Wi-Fi, most homes have Wi-Fi, most businesses have Wi-Fi, and the benefit is we can take a computer like this guy right here that has a built-in network interface card that's using Wi-Fi signals, which is just radio frequency, to connect to the network. Very, very convenient. You don't have to have a physical wire plugging us into a switch. However, it is important to know what device on the network is sending and receiving that Wi-Fi that allows this customer to connect. And the answer to that is something called an access point. The acronym for an access point is simply AP. An access point would generally connect into a switch, so there's a wired connection from the switch to the access point. And the access point is responsible for the sending and receiving of these radio frequencies so that devices like Computer 3 can associate with an access point, authenticate, and get connectivity into the network. And these access points have lots of different flavors. They have some that focus the direction of the radio frequency signal in a certain direction. That would be an example of a unidirectional antenna. And they have some that simply emanate the signal in all directions around them. And that would be an example of an omnidirectional antenna. And we'll cover more when we talk about specific nuggets on wireless. And in a home network, it's very likely that if you have a router, there's very likely the access point, the Wi-Fi capability that's integrated into that home router. So for a home router, it might look like this. We might have a connection that's labeled WAN or Internet. That's the one we plug in to our internet service provider's gear. That may be DSL, or it may be cable modem that goes off to the internet service provider and the cloud, the internet. And generally they have 4 local area network ports. These would all be for connecting devices inside your home. And these are simply layer 2 switch ports. So as you connect devices to these ports, let's say we have PC 1, 2, 3, and 4. Each of these 4 computers has their own MAC address. That's the layer 2 address. And with the layer 2 switch, if PC 1 and PC 3 are communicating with each other, the layer 2 switch only forwards those frames of data to the ports that need that information. Now at the same time, this box is also doing routing. So it's also acting as a layer 3 router, because it's routing between this internal network where your 4 computers are and the wide area network, or the WAN connection, or the internet connection that goes off to the service provider and leads towards the internet. And the way we got started on this whole discussion was the fact that this access point could be integrated into this router. So with antennae that could be either internal to this box or external, there may be 2, there may be 3, there may be 4, depends on the model. That would be adding the additional Wi-Fi capability so that inside your home, you could have devices, for example, device number 5, which is wireless, which would now have access to your local area network. But instead of having to use a cable, it's connecting through the access point that's integrated as part of your home router. And for the routing part, these 4 ports and this access point here, these would all be, for example, network G, just to label it as an IP network. And then this port would lead off to a different network, including the internet. So the layer 3 routing is done between your internal network at home and the wide area network, or the internet connection that's being provided from your service provider. So for example, maybe this is network H over here. And the layer 3 routing is doing routing based on IP addresses between 2 IP networks. In this nugget, we've discussed the function of 3 additional components in our network, including a packet shaper, content filter, and an access point. I appreciate you joining me for this nugget. I hope this has been informative for you, and I'd like to thank you for viewing.